Hi guys, today we will talk about syntax analysis. As we all know, the first phase is lexical analysis, but we will focus on the second phase. Syntax analysis or parsing in the second phase of a compiler. In this video, we shall learn the basic concept used in the construction of a parser. We have seen the lexical analyzer can identify tokens. Syntax analysis or a parsing is the second phase of the compiler. In this video, we shall learn the basic concepts used in the construction of a parser. We have seen that lexical analyzer can identify tokens with the help of regular expression and pattern rules. But a lexical analyzer cannot check the syntax of a given sentence due to limitation of the regular expression. Regular expression cannot check balancing tokens, such as parentheses. Therefore, this phase uses context-free grammar or CFG, which is recognized by push-down automata. Let's discuss the context-free grammar. In this section, we will first see the definition of context-free grammar and introduce terminologies used in parsing technology. A context-free grammar has four components. First, a set of non-terminals. The symbol is letter V. Non-terminal are syntactic variables that denote sets of strings. The non-terminal define sets of strings that help define the language generated by grammar. That as non-terminals. Next is a set of tokens, known as terminal symbols. The symbols is sigma. Terminal are the basic symbols from which strings are formed. The next one is a set of production. The symbol is letter P. The production of a grammar specifies the manner in which the terminal and non-terminals can be combined. To form strings, each production consists of a terminal called the left side production. Next is one of the non-terminals is designed as start symbol, from where the production begins. So, let's take an example. We take the problem of a palindrome language which cannot be described by means of regular expression. That is, L is equals to W or W is equals to W over R. It's not a regular language, but it can be described by means of CFG. As we illustrated, G is equals to V, sigma, P, and S, where V is equals to Q, Z, N, sigma is equals to 0, 1, P is equals to Q to Z, or Q to N, or Q to epsilon, or Z to 0Q0, or N to 1Q1, and S is equals to Q. This grammar describes palindrome language, such as 1001, 111, 0011, 00100, 1010, 101, 111, etc. Now, let's talk about the syntax analyzer or parser. This takes the input from a lexical analyzer in the form of token streams. The parser analyzes the source code against the production rules to detect any errors in the code. The output of this space is a parse tree. This way, the parser accomplishes two tasks: parsing the code, looking for errors, and generating a parse tree as the output of the phase. Parsers are expected to be parse the whole code even if some errors exist in the program. It is a sequence of production rules. In order to get an input string during parsing, we take two decisions for some essential form of input which are deciding the non-terminal
that is to be replaced and deciding the production rule by which the non-terminal will be placed. To decide which non-terminal to be replaced with production rule, we can have two options, which are the left and rightmost derivation. If the essential form of an input is scanned and replaced form to left-right, it is called leftmost derivation. The essential form derived by the leftmost derivation is called the left essential form. Production rules. E to E plus EE to E times EE to ID. Input string ID plus ID times ID. The leftmost derivation is E to E times EE to E plus E times EE to ID plus E times EE to ID plus ID times EE to ID plus ID times ID. Notice that the leftmost side non-terminal is always processed first. But if we scan and replace the input with production rules from right to left, it is known as rightmost derivation. The essential form derived from the rightmost derivation is called the right essential form. The rightmost derivation is E to E plus EE to E plus E times EE to E plus E times ID, E to E plus ID times ID, E to ID plus ID times ID. Now, a parse tree is a graphical depiction of a derivation. It is convenient to see how strings are derived from the start symbol. The start symbol of derivation becomes the root of the parse tree. Let us see this by an example from the last topic. Take note that all leaf nodes are terminals. All interior nodes are non-terminals. And in order traversal gives original input string. So step 1, E to E times E. For step 2, E to E plus E times E. Step 3, E to ID plus E times E. Step 4, E to ID plus ID to E. Step 5, E to ID plus ID times ID.
A parse tree depicts associativity and precedence of operators. The deepest subtree is traversed first. Therefore, the operator in the subtree gets precedence over the operator which is in the parent nodes.